Welcome to the deep dive. Today, we're looking into what is, I guess you could call it, a planetary tragedy.
A cold case almost.
Yeah, the death of Mars. We're going to focus on the ESCAPADE mission, which sent these two really small but incredibly ambitious spacecraft to get to the bottom, the biggest question about the red planet.
And that question really is, what happened? I mean, we have so much evidence that Mars was once warm and wet. It had seas, it had rivers, probably clouds.
Yep.
It was, a potentially habitable world.
And then something went catastrophically wrong.
Exactly. The atmosphere was just stripped away by some invisible force.
Yeah.
And these twin messengers, Escapade Blue and Gold, which I love this detail, are no bigger than office refrigerators.
That's amazing.
They're up there right now, watching the planet's slow-motion demise as it happens.
It's like observing a crime scene while the crime is still in progress. So let's jump right in. Why did this happen? It all goes back to the sun, right?
It always does.
Hmm.
The main threat here is the sun's constant output, what we call the solar wind.
And this isn't just, a gentle breeze.
Not at all. It's a storm, a constant storm of charged atoms, protons, electrons flying outwards at millions of kilometers per hour. If a planet doesn't have protection from that, it's just going to get shredded.
And Earth has the perfect protection. Our global magnetic field. It's like a giant invisible force field that just pushes all that harmful stuff aside.
Right, it deflects it. And what's so fascinating and kind of tragic is that Mars used to have one too.
Yeah, it did.
Yeah, but billions of years ago, its core cooled down. That internal engine, the dynamo that generated the field, it stalled. And when that happened, the global magnetic field collapsed.
The planet's shield just vanished. But I remember hearing that some bits of it were left behind, like little magnetic pockets.
That's right. Those are the tattered remnants.
Hmm.
All that's left are these small, very localized patches of magnetism that are literally locked into the ancient rocks in the crust.
So instead of one big planetary shield, it has a few scattered magnetic umbrellas.
Which do almost nothing against the full blast. So the solar wing, with no global shield to stop it, just started slamming directly into the atmosphere, ripping it away, molecule by molecule, for billions of years.
And now we're left with this thin, cold desert. And ESCAPADE's job is to measure just how fast that ripping process is happening today.
Precisely. They're measuring the battle as it happens.
Yeah.
And what's so revolutionary about it is how NASA even got them there. This mission, it signals a huge shift in thinking.
Yeah, because for so long, space science meant these huge bus-sized probes, giant budgets, and development cycles that could last a decade or more. ESCAPADE just threw that playbook out.
It's a whole philosophy of what they're calling scientific agility.
Right. Lighter, faster, more efficient.
Exactly. They built these spacecraft to be incredibly capable, but they used commercial off-the-shelf parts where they could. They proved you don't need a truck-sized machine to get world-class science.
And the launch vehicle was a huge part of that story, too. They didn't go with a traditional rocket.
No, these two little refrigerators flew on Blue Origin's Nuke Land, a heavy-lift rocket from a commercial company.
That's a huge vote of confidence. NASA handing a major science mission over to commercial innovation, it just makes getting to space faster and cheaper.
It shows the whole ecosystem is changing. The science community is now really leveraging the speed of the private sector.
So let's get into the science itself, because the design of this mission is it's genius. The fact that there are two of them.
This is the absolute core of it. They're identical in terms of their hardware. They both have magnetometers on these long, skinny booms and plasma analyzers to basically taste the charged particles going by.
But they're not doing the same job.
Not at all. They're in two different parallel orbits.
So you have blue flying low and gold flying high. What does that difference in altitude actually tell you?
It gives you the third dimension. It's crucial. One spacecraft flies lower, really skimming the atmosphere where the solar wind pressure is at its most intense. That's the boundary layer. The other one sweeps higher, way out, mapping the bigger, more complex magnetic structures that stretch out into space.
So instead of a flat picture from one point of view,
You get a stereoscopic view, a 3D movie of the whole system in action.
that makes sense.
Because think about it. If you only have one spacecraft and it detects a change, you don't know what happened. Did you fly through a stationary cloud of plasma? Or did a wave of plasma just wash over you?
Right. You can't tell what's standing still and what's moving.
But with two of them, watching the same event from two different spots at the same time, you can tell the difference between a static structure and a dynamic traveling wave.
And they're tracking the actual atoms that are escaping, aren't they?
They are. Specifically, they're looking for hydrogen and oxygen ions.
The building blocks of water.
Exactly. When Mars had oceans, those atoms were locked together as H2O. Now, solar radiation breaks them apart in the upper atmosphere, and the solar wind just carries them off into space. Every single one they detect is, quite literally, a piece of a lost Martian ocean.
That's incredible. So to get this perfect scientific setup, they had to survive the journey there, the cruise phase. We kind of gloss over how hard it is just to get from A to B.
It's months of just pure vigilance. The spacecraft had to do this very slow, careful rotation, like a pirouette in deep space.
To keep the temperature stable.
And for power.
Yeah.
Yeah, and then you have the trajectory correction maneuvers, the TCMs.
Right, the little course adjustment.
And these aren't like steering a car. It's more like trying to balance a pencil on your fingertip while walking. Tiny, tiny burns from small thrusters, just to nudge them into the perfect corridor to meet Mars millions of kilometers away.
And all of that leads to the most nail-biting moment, Mars orbit insertion, the MOI.
Oh, it's the ultimate moment of tension. Because of the vast distance, there's a huge time delay in communications.
So the team on Earth sends the command to fire the brakes.
And then they just wait. For agonizingly long minutes, they're literally watching the past, waiting for the signal to tell them if the burn worked, or if their mission just flew right past Mars. Success or failure is only revealed after it's already happened.
I can't even imagine the stress in that room.
But they made it. And the second they were captured by Mars's gravity, they were in the thick of it, observing the bow shock.
That's the wake that Mars creates in the solar wind, right?
It's the invisible front line where those supersonic particles slam into the atmosphere and slow down. They see the plasma tails, the vortices, all of it happening in real time.
Okay, so they're collecting all of this high-resolution 3D data. What's the biggest truth that ESCAPADE is showing us that maybe earlier missions like AVEN couldn't see?
The biggest thing is probably the mechanism of the atmospheric loss. The old idea was that it was a fairly steady, slow trickle over billions of years.
A slow leak.
Right. But ESCAPADE's data, that 3D movie, it's showing that the loss is not steady at all. It's actually dominated by these violent episodic events.
So it's not a leak, it's more like getting hit with a sledgehammer over and over.
That's a perfect way to put it. When a big solar storm, a coronal mass ejection, hits Mars, the rate of atmospheric loss just spikes. It can strip away huge chunks of the atmosphere in just a few days.
Wow.
And by measuring those events, we can get a much better estimate of how quickly Mars really lost its water. It helps scientists calculate how long it could have actually been habitable.
That completely changes the timeline. So let's bring it home. Why does this matter to us? I mean, why should you, the listener, care about the physics of a long-dead planet?
Well, for one, it's just critical for future human exploration. If we're going to send people there, we have to understand that radiation and plasma environment, especially during these sudden solar storms, it directly affects how we design habitats, suits, everything to keep astronauts safe.
So it's a practical safety issue. But it's bigger than that, isn't it?
Well, absolutely. This gives us a deep insight into the delicate balance any planet needs to hold on to its atmosphere. When we look out at exoplanets around other stars, this tells us what to look for. How strong does its magnetic shield need to be? How resilient is its atmosphere?
It's the ultimate case study.
It is. Mars shows us just how fragile a habitable world can be and how quickly it can be lost to these invisible forces.
That's such a powerful takeaway. These two little messengers, the size of refrigerators, gave us this unbelievably complex 3D picture of Mars's environment. They've really given a voice to the silent forces that decided that planet's fate.
It really is proof that big science doesn't always need a big machine.
So here's the thought for you to carry forward. ESCAPADE has shown us that planets are not static relics. They are active, fragile systems in a constant, often violent struggle with their star. So what does the fate of Mars and this discovery that its atmosphere is torn away in these unpredictable, catastrophic bursts, what does that teach us about the long-term survival of any habitable world, including our own, in a solar system that is anything but gentle?